If you understand the movement of electrons, organic chemistry will make a lot more sense. Let's review some of the characteristics of electrons you learned in general chemistry. On a single atom, electrons occupy atomic orbitals. Recall that there are s, p, d, and f orbitals, and in organic chemistry we will almost exclusively be concerned with s and p orbitals. S orbitals are spherically shaped, and p orbitals are shaped like a dumbbell. In molecules, things get a little more complicated, so to simplify things, we make use of valence bond and molecular orbital theories. Valence bond theory is what you are probably more familiar with. Electrons in orbitals on adjacent atoms overlap and form a chemical bond. To get the atomic orbitals pointed in the right directions to form the chemical bonds, valence bond theory employs hybrid orbitals. Mixing s and p orbitals yields sp orbitals that would yield a 180-degree bond angle. sp2 orbitals that would yield 120-degree bond angles, and sp3 orbitals that would yield 109.5-degree bond angles. The bonds that are formed by the end-to-end overlap of atomic orbitals are called sigma bonds, and those bonds that are formed by a side-to-side overlap of p orbitals are called pi bonds. We will make extensive use of valence bond theory as we discuss the formation of new bonds. Molecular orbital theory will be more useful when we discuss electronic energies of molecules, such as conjugated dye molecules and aromatic compounds. Molecular orbital theory is very similar to hybrid atomic orbitals. When we make hybrid atomic orbitals, we start with a few atomic orbitals and we mix them together to make orbitals with different shapes. Similarly, in molecular orbital theory, we start with all of the atomic orbitals in all of the atoms in a molecule and mix them all together. The result is a set of molecular orbitals. So in molecular orbital theory, electrons do not exist in localized bonds. Rather, they belong to orbitals that span the entire molecule. This picture is useful when addressing questions about energetics and spectroscopy, but less useful when addressing questions about mechanisms. Let's end by examining water. Since there are 4 electron domains, the oxygen atom is sp3 hybridized. 2 of the sp3 hybrid orbitals on the oxygen atom form sigma bonds with the s orbitals on the hydrogen atoms. The remaining electrons are placed in non-bonded sp3 hybrid orbitals on the oxygen atom. According to molecular orbital theory, we combine the s orbitals on the hydrogen atoms with the s and p orbitals on the oxygen atom to arrive at 6 molecular orbitals that look like these. Notice that as the energy increases, the number of nodes, locations where the wave function is 0, also increases. The highest energy molecular orbitals, those with nodes between the atoms, are anti-bonding orbitals. The lowest energy molecular orbitals, those without nodes between the atoms, are bonding orbitals. The remaining orbital is considered a non-bonding orbital.